Okay, so let's pick up where we left off, shall we? Yeah, no. There we go. Does it look familiar? So I promised you guys to go over ghost classes. And so you're probably thinking, okay, great, what is this, right? What kind of a Fruit Loop journey is it going to take us on now? I've got no end of Fruit Loop journeys, by the way, so just get used to it. Right, so the whole point of this one was to kind of drive home the point about how revolutionary and kind of watershed this moment was in history, right? And we kind of talked a little bit about their perspective, right? The idea that they didn't have any sense of reality beyond what they could see visibly, right? And so the thing that I wanted to do was do for us what a similar invention would look like for us. And for us, it would be ghost classes. So I want to do an Anton van Leeuwenhoek. I want to invent something that allows us to be able to see something we can't currently see, right? So for the most part, ghosts are not visible, right? Unless you're like, got some other thing going on, and that's a different channel. But basically, when you want to take a look at this, first of all, let's define this. Let's just think about this and kind of frame it a little bit before we actually invent it. So if you think about how many people have been on this earth, how many people are here now, right? About 8 billion or so, right? And moving up, right? And now think about how many people have been on the earth in the past. Hundreds and hundreds of millions. So there's been a lot of people on this planet. So the question is then, even if we basically say that 10% of the folks that die kind of stick around and wander about restlessly, that 10% is still a pretty astronomical number, right? So when we're talking about ghosts, we're not just talking about the occasional ghost walking around. We're talking about lots of unseen people walking around. Okay, so that just kind of frames perspective we're talking about here. Because you always watch these ghost hunter shows, right? And they go to all the creepiest places. Notice they always turn the lights off. I'm pretty sure the ghosts don't care if the lights are on or off. So that's kind of a little thing. It's like, why do you have to turn the lights off, right? So that tells me more about you than about the ghost, actually. So they're also, when you take a look at them, it's like pulling teeth, right? I mean, they go through, house to house to house, room to room. I mean, they're there all night long, and they might get a little bit of a smattering, some crazy static pattern that they think is a voice or something like that, right? I mean, so they kind of make it look like this is very far in future, like it's hunting for Bigfoot, right? But let's say that the ghosts are much more common than you expect. Oh, by the way, another problem with ghostology is they're not aloof, right? In this scenario, they're not aloof. So like, for instance, when you're taking a look at one of these shows, you always kind of see the sort of aloof apparition, right? That just kind of like walks in, doesn't even notice you're even there. Just kind of like there's some sort of time loop or something like that. They're just kind of like a film. They're just sort of aloofly walking by. They don't even recognize you, right? That you're even there. No. That's what we're talking about here, right? We're talking about ghosts that are interactive. I mean, they're sitting there, they're making eye contact with you. They're like, right? They're trying to like get your attention. They see you, right? So this is a different breed of ghost. Okay, that's what we're talking about. Lots of them and interactive. Now, let's invent the ghost classes and put them on. So instead of seeing an empty room, what you see is actually a room full of people. So you see basically all these apparitions. They're all sitting around. There's a couple hovering over your shoulder right behind you. They're kind of looking around. They're kind of looking, trying to figure out what you're doing. Some of them are trying to talk to you, right? Just like we always try to talk to them. Are you here? Did you die suddenly? Right? I mean, this is like what those ghostology people do. But that would be a little creepy, right? because now all of a sudden everybody can see ghosts. But guess what? That's not far enough, because that's not really to scale about how this kind of changed their view of the reality that they had back in the day. Let's imagine we go one step further. Let's imagine it's morning. You wake up and your plan is to take a quick shower to get the day started. So you go and do the bathroom, you disrobe, as one often does before they get ready to take a shower. And there you are, standing buck naked, getting ready to turn the water on. But wait, let's put the ghost glasses on just for 1 second. And what do you see? You are not alone, right? And it's not just a few people. There's a whole bunch of people there. There's like 3 people in the shower already. And they're looking at you. They're like, right? There's one dude sitting on the can, another one at the sink. And there's a couple of people behind you. And they're all looking at you like they're trying to communicate with you. And here you are, naked as a jaybird. Yes. So, what are you likely going to do? Yeah, you're going to put your clothes on pretty quickly, right? You're going to be like, you know what? I think I'm going to pass today. I might get a little gamey at the end of the day, but you know, I'm okay. I'll figure some other way. Maybe I'll start taking my showers at a car wash. Yeah, but I'll just keep my clothes on, right? And just kind of walk through the car wash, because I can just let the clothes dry and I'm good. Would that be a little creepy? Would that change your perception of reality? Oh no, let's make it worse. Let's imagine you and your significant other go out for an evening on the town. You guys have a great time. But as all great evenings often do, you end up at home and you want to spend some intimate time together. So one thing leads to another. You retreat to the parlor of love, better known as the bedroom. And of course, as things occur in those circumstances, you both find yourself disrobed and ready for the deed. Oh, but wait. Let's put on the ghost glasses first. What do you see? You see a lot more than you want, right? So there's already one dude laying on the bed. There's another guy, Uncle Charlie's right there. The pedophile that died in jail. There's another dude over here that's kind of like looking at you like, right? And then there's one dude on the bed like this. Ready. That's a bit of a showstopper, yes? Did that just kill the moment? I mean, unless you like to be watched, you know, most people are like, you know what? We had a good night. Let's call it a night. I'm gonna take these ghost glasses off now. Uncle Charlie, please don't ever show up again. Right? The birth rates in this country will go way, way down, wouldn't they?
Want to be watched.
Yeah. Yeah, right. So obviously, is that going to change your perception of reality? It's going to change the way you do things, right? It's already changing your bathing habits. It's changing those moments when you're like alone. You got me time. Guess what? That me time isn't me time anymore, is it? You're never alone. Whether you can see them or not, you're never alone, right? And they follow you like paparazzi. And not only that, but you can't shut them out. You can't lock them away. You can't go hide in a room, right? Because they can go through the door. So there's nowhere you can escape. So would that change the way you live your life? Yeah, by a lot, wouldn't it? Many of us would get paranoid, only we'd stop calling it paranoia, because paranoia is basically being afraid of something that's not real. In this case, it's actually real, right? So like, I'm only paranoid if it's not true, right? In this case, it is true. So it's not paranoid anymore. It's justifiable fear. So obviously that would change, completely radicalize our perception of reality. That's kind of what happened here. So this is what happened to these guys. That microscope basically radicalized their entire perception of reality and the way they thought about things and whether things were alive, right? It challenged everything you used to know. And remember, we mentioned up before this, that what you knew at this point was largely driven by theology. That's kind of your framework. That's what you had. And so you kind of have a total reordering of the perception of life and reality from a theological framework to now more of a natural framework. And people honestly didn't know what to do with that. And those kind of moments really happen. This is the reason why I say of the big three watershed moments in society that sort of created a before and after effect, right? The nuclear bomb, evolution, and this is by far the biggest of all three. Because it just completely just turned us upside down. So then from the 17th century, then what we get is basically a bunch of rich people buying this toy because it's cool. It's like the Rubik's Cube of its day. It's like the fad thing for all the glitterati, right? You had to have one. Anyone who's somebody has to have one, that kind of thing. And a lot of the aristocrats, you know, a lot of them just, it was a toy. So they looked at stuff, it was kind of cool, it was a little bit of a parlor game. But then there were some that took it seriously, like Robert Hooke, for instance, took it seriously. That's the reason why he's the father of cell biology. And there's others that took it seriously as well. And they didn't just sort of play with it, they actually wrote stuff down. So they actually drew sketches and they drew pictures and they said, this is what I'm seeing, this is what I'm describing. So they actually try to do a good job of documenting everything that they were seeing. And so this is kind of like the genesis of cell biology. Now, one thing I want to point out, that's not so much vast conspiracy of inequity as much as just the way history was back in the day. If you notice back in scientific history, most of the big scientists are all a bunch of rich white guys. And they're usually lords and this and that and barons and that sort of stuff, right? I mean, so they're like, they got title. They're rich white aristocrats. And Robert Hooke himself was a white guy. And there's a reason for that. Because back in this day, if you recall, when we kind of sketched out society, you really had two types of people, the haves and the have-nots, right? There wasn't like a middle class. That didn't exist. That's actually, we're kind of spoiled actually in this generation because we actually think that the middle class is a right when you have to work your ass off to create a middle class. And it actually is easy to lose it. It's very difficult to create it. And this is the reason why there's so much political chatter about that, about the idea of putting too much burden on the middle class, because most of humanity never had it, right? So most people like us, just average people, non-rich people, we wouldn't have been in the nice cushy confines that we're in. We would have basically been on the streets, scrounging about in the alleyways, looking for our next meal. That's what we would have been doing. That's what people did in this day, right? So they were basically desperately looking for how to feed my family, how can I actually make a living, right? Scratch out an existence. And then on the other side of the Great Divide was the complete photo negative of that. A bunch of people who were rich, lots of money, entitled. Because back in that day, there were no such thing as a Jeff Bezos. There was no such thing as a Mark Cuban, right? These are self-made billionaires at this point, right? Who were not billionaires when they were born, right? America is sort of the phenomenon in human history. We kind of think that this is normal. This is absolutely not normal at all, right? So there was no such thing as a self-made millionaire. There was no middle class. There was nobody who pulled down 100K, a year, who was able to sort of afford a suburban lifestyle. Those didn't exist. If you had money, it's because you are an aristocrat and you had family wealth. Those are the only rich people around. There was no way whatsoever to get rich. None at all. That's kind of desperate if you think about it, right? That's one of the great moments of America that we hugely take for granted, which drives me insane because most Americans act like a bunch of spoiled brats, completely blind to just how uniquely blessed they are, because nobody has it or has had it as good as we have it. Even on our worst day, we live like the kings back in this day. So basically then the normal folks like us, we would be worried about other things. I mean, we're just simply trying to feed our families. We're trying to earn a living. We're trying to, take care of our kids. If they got sick, God help us, because there's no doctors around. There's really no medicine around. I mean, it's basically what you've got is just a bunch of prayers and hopes. That's all you've got when you got sick. And life was desperate and life was brutal, right? I'd say the average American probably couldn't cut it living in this time frame. We're too soft. I mean, just think about it. We fell apart when we ran out of toilet paper. It's like, are you kidding me? The crybabies are crying when you lose your freaking toilet paper. This is your crisis. To me, that was like the most shameful moment in my life. I was almost afraid to admit I was an American. I mean, that was just absolutely disgraceful, especially when you consider what other people in this world have to live with on a day-to-day basis. I mean, it just kind of made me sick, actually. So just think about that. Don't complain about toilet paper to me. Right? So how about the rich people? What did they do? We already know what the poor people do, right? They're busy trying to survive and they're trying to feed their families and their kids and that sort of stuff, keep them alive, right? I mean, that's no joke back in those days. So what do the rich people do? Well, they're pretty useless, actually, as it turns out. I mean, you're rich, you got a lot of money, you've got a lot of time, so you're not really all that useful to humanity, are you? I mean, what are you doing? Honestly, you're kind of a waste of skin at that point. So most glitterati back in that day pretty much did one of two things. They either fought wars with each other, which they did a lot of, or they pursued some sort of a scholarly endeavor. There wasn't really a whole lot else you could do with your discretionary time and money. That's the reason why a lot of these early scientific pioneers are rich, titled white guys, is because they were the only ones that had the time and the money to pursue these sorts of endeavors. The rest of us were desperately just trying to survive. Okay. So it's good to live in the 21st century because it can be worse, much, much, much worse. Okay. So notice the time spread here, right? So basically we have about 200 years or so, give or take, from the time that Robert Hooke was around, the 17th century, late 17th century, to when Schleiden and Schwann, two cell biologists in the 19th century, basically pulled together all of these observations. So we have actually 200 years of work in cell biology. So lots of different people from lots of different titled families looking at this, and some of them are doing a great job of recording it. And Schleiden and Schwann themselves looked at their own stuff as well, and they pulled together all these observations from all these folks that are looking at all these different things. And what they drew basically was a couple of about 3 different major postulates. So this is all the cell theory, which is basically derived by inductive reasoning. Remember inductive reasoning from chapter 1? Do you? What is inductive reasoning? Remember the analogy, the example that I gave you of inductive reasoning? I had you guys all go outside and tell me the color of? Yeah, right. Many observations over time basically accumulate to give you the ability to make a sound prediction on. That's basically what happened here. Yeah, generally it's like, it's got a legal version of it, right? Preponderance of evidence, where any one circumstantial thread of evidence isn't enough to convict, but if you have a whole pile of circumstantial pieces, the more you have, the heavier that weighs on you, because an innocent person may pick up 1 or 2 of those threads, but a guilty person would basically fit all of them, right? So the more of those you can hang on you, the more likely it is that you actually did it. That's the preponderance of evidence. And in this case, the more observations you make, and they all are in harmony with each other, then the more likely that that particular idea is true, right? So for instance, the sky was the example that I gave you guys. I said, go outside and tell me what the color of the sky is. And you all said confidently that it is, right? So if I asked you to stake your life on it, you would confidently say. So that basically means that you're pretty convinced that it's blue. That's inductive reasoning. So you've made a conclusion based on not an experiment. You've never done an experiment to test the blueness of the sky, right? It's simply based on the millions at this point of observations that you've made in the sky. You've never seen the alternative to be true. Okay. That's inductive reasoning. So basically what Schleyman and Schwann did was they took all these observations over a couple of centuries and they pulled them all together and they looked for these kinds of inductive postulates where they could say, listen, these are clearly emerging. These are something that we're seeing overall. A couple of things I want to mention and that I want you to kind of pay attention to, kind of a little bit of my historical twist, is notice the time frame that they're doing it. 1838, 1839. So they're basically in not just a little shy of mid-19th century. Just to give you an idea in context, first of all, a lot of times the 19th century is sort of seen as very much the sort of the unsexy century, right? So it's the uninteresting one. It's the era of Victorian. Again, she was pretty dry. I mean, the Victorian era in terms of British ethic, and it was pretty dull. That's where you get your British dullards, right? I mean, that's that thing that comes out. So we think of the 19th century as a pretty boring century. But in reality, the 19th century is really critical because what happened in the 19th century set the stage for the explosion that happened in the 20th century, right? If you think about the 20th century, there's not been a moment in human history like the 20th century ever before. We started the century in 1900 riding horses. We ended it fretting over Y2K. And computers and global networks and internet crashes. That's what we ended with. So the level of knowledge from 1900 to 2000 was exponential. It was an explosion of knowledge. So basically the scientific flower was blooming and blossoming, and now we're in full bloom. So the question is, how did we get there? I can tell you how we got there, the 19th century. Just like a blooming flower, you're never going to get a blooming flower unless you plant the seeds first. Yes.
My history teacher from last semester would say, like, if you take someone from 900 and drop them in 1400, they would probably do all right.
Yeah.
Drop them in 1600, they'd probably do all right. Drop them in the 1900s and they're completely lost.
Yep. And that's true, right? Because you can actually see that you don't even have to go back that far. You could say, even if you drop somebody from 1700 to 1800, life was largely the same, right? 18 to 19, a little bit of change, but for the most part, you could probably still figure yourself out. I mean, it's like you're in a different world when you go from 19 to 2000, right? But all those seeds for that explosion of knowledge were all planted in the 19th century. This is the reason why the 19th century is so critical. But it's really kind of like I say, it's the unsexy part of it, right? Because think about it. When you're growing stuff, you don't get excited about the dirt, do you? It's like, whoa, look at that dirt. Oh my gosh, I'm getting so excited. No, it's the flower that you get excited about, right? But we all know that in order to get the flower, we have to put in the work. You have to have a dirt patch. It's not very interesting at all. You have to put a seed in there and you see nothing for a long time, right? You just kind of water it, you hope, and water it and hope, and water it and hope, and then someday, if you get lucky, you'll start to see a little green thing come out, and you get all excited, right? But then once that little green thing comes out, I mean, it's fast, isn't it? It's starting to shoot up, and then it goes for you, right? This is exactly what's happening in the 19th century. It was the dirt patch of science. It was us planting seeds in science. There's a lot of things that are swirling around this particular moment. And this is the reason why I want to couch this, because it's critical to understand globally what's going on in science, because a lot of our major scientific divisions are being born at the same time. At this time, not only is Schleiden and Schwann pulling together the cell theory after hundreds of years of observation, but also at this time, Darwin had already completed his voyage on the Beagle. I think that was about 10 years prior. And so he basically was it's also, this is before he wrote his paper on the transmutation of species by natural selection, which is the evolution paper. That comes in 1859. So he's a couple of decades away from that one. So at this point, Darwin is sort of sitting in his lab with all this stuff that he collected on his voyage, trying to sort it all out and make sense out of it all. So this is really kind of the formative period that is leading up to the ultimate presentation and introduction of the idea of evolution by natural selection that Darwin proposes. At this particular time, to kind of tie up that theological aspect that we started here in the 17th century, by the time we get to the 19th century, theology was still around. Obviously, it still is. It'll never go away. It's just part of our fabric. It's kind of who we are. But basically, it had been changing a little bit at this particular point as we led up to it. We all are very familiar with kind of the wars that creationists and evolutionists have had throughout the 20th century. But a lot of that war is on the age of the Earth, right? So for the first time, we kind of started really thinking about, well, wait a minute, how old is all this stuff, right? I mean, we're starting to find fossils. Paleontology is starting to become a thing. We're starting to find all these bones of things that don't exist anymore. And we're trying to figure out what's happening, right? And so naturally, we ask a lot of curious questions like, well, wait a minute, what is this big, giant, mean-looking lizard thing? I mean, when did this live? I mean, I don't see this anywhere, right, in human history recorded. You'd just think that if somebody saw this, that they would write it down, right? So it's like, oh, big lizard, eats meat, look out, right? So you see something in there, right? And so obviously that's what's happening right in this area. There's also a lot of geology happening. So Charles Lyell, the father of geology, is right around the same, a little bit before. And he's coming up with some of the basic principles in geology that sort of lays down this idea of old Earth. But the Earth is a lot older than we originally thought that it was. And ironically, at the same time, some denominations on the theological side of things are coming to a similar conclusion. So it's actually not correct that the concept of an older is purely a scientific one, because some of the denominations at this particular time were also coming up with some ideas that Earth is much more older than we originally thought. And so some of that is sort of swirling around. The reason why I say that is because all of that is kind of swirling around in this particular era, along with geology, as we're trying to go out there and understand, like, how did the Grand Canyon get made? Right? How did the Grand Tetons get made? How did the Himalayas get made? So we're out there in the world now, we're looking at this, and we're trying to figure out, how did this all come to be? And all these different ideas are swirling around, and they all feed, and they kind of germinate a little bit right at the same time when Darwin is sitting down and pulling together his thoughts and his ideas. So that's important, right? Because you don't just come out with an idea out of thin blue air, right? It's always usually a product of multiple different ideas that are swirling around that kind of mutually support each other. And so usually, no person stands on their own. And of course, all of this was also swirling around at that time as well. So Darwin was focusing on animals, organismal things, and Schleiden and Schwann were focusing on cellular things. So you could see this kind of continuity of life. And so the important thing then with that perspective, and I want to make sure that you hit that we get that perspective, because it makes the cell theory make a little bit more sense in context. So what is the cell theory? What are the parts of the cell theory? There's three parts. Number one is all organisms are composed of cells. That is to say, everything that's alive is composed of cells. Now, first of all, remember, over the last 200 years, this is like no joke, it wasn't easy to define life, right? Because remember, we go from the 17th century where life is largely defined by a theological framework, right? Soul and all that kind of stuff, to now trying to figure out, wait a minute, how do we redefine life from a more naturalist point of view, right? So that is not, kind of separating it from the theological concept. And that wasn't easy at all. Like, here's an example, right? Are you alive? Okay, you're pretty comfortable with that. How do you know? Okay, great. So you're responding, right? So and a heartbeat, right? Because you can't respond if you don't have a heartbeat.
Plants don't have heartbeats.
Exactly. Are they alive?
Yeah.
Okay, we're pretty comfortable with that, right? But notice, now we have to change our criteria, don't we? So we can't use heartbeat to define life because we have things that are alive that don't have hearts, right? So then how do we define being alive? It's like, okay, so I respond, right? That's a good place to start, right? If we blow that up a little bit, then what do we say? What are you responding to? Well, you respond to the environment. And typically you are answering one of those big biological questions of life, right? So do you grow? Do you develop? Do you have an energy plan? Do you reproduce? Now, we didn't like lay out these big biological questions of life, by the way, and say like, okay, here's my criteria for life. Now let's go out and find things that are alive and not alive. It's not alive. That's not the way it works. We actually built the big biological questions of life, like through trial and error and hard pain and suffering through this process. So as we grappled with things and saying, well, I don't know if it is alive, right? I mean, and then as we sort of wrestled with that, then we said, well, it is alive. Why? Because it's answering this big biological question of life. So if it wasn't alive, it wouldn't be able to do that, right? And so that's how we kind of built that big biological questions of life list. And so ultimately now we get to the place where pretty much if it's alive, it is made of cells. Yep.
But are cells alive?
Yes, that's the next one, right? So basically the smallest living system is a single cell. So basically we refer to this as the basic unit of life. What does that mean? Yep. Smallest we can get and still answer all the big questions of life. If we get any smaller than this, we can answer some of them, but not all of them. We have to be able to answer all of them, right? So this is the smallest we can get and still be able to answer all those big biological questions of life. Yep.
Then are the cells that make us up, like make up us, like are they considered alive separately from us?
No, that's a little bit of a criteria that's downstream, right? Because what they've done is they've given some things up in order to work as a cooperative. So just like, if we're going to form a team, then I have to make room for my teammate, which means I have to give up some space and I have to let some things go, right? And that's part of it. So, I mean, are they alive? I mean, they're alive in a sense, but they're not alive like a protist, for instance, who's fully free living, right? We have a term in biology for that, free living versus not free living. Our cells are alive, but they're not free living. They can't answer all the big biological questions of life without us protecting them as a colony of cells. That makes sense? So, okay, and the third and final one is a yeah, duh moment. Basically, cells arise only from pre-existing cells. A lot of times students stop at that one. They're like, wait a minute. Why would that one be this great cell theory component, right? I mean, you're looking at that one, you're probably thinking, well, where else would they come from, right? I mean, after all, think about it. Where do puppies come from? Yeah, dogs, right? Where do kittens come from? Yeah, where do the babies come from? People, right? So where else would cells come from, right? This is like, we learned this one, what, when we're 2? So where else would they come? Is this kind of a yeah, duh situation, right? It's like, yeah, duh. Where else? What? I mean, why would you waste your time, vaunted cell theory, on something so trivial? Oh, but wait, it wasn't trivial. You know what they're trying to do with this one? Because back in the 19th century, about this time, there was an idea called spontaneous generation. It was an idea of origins, right? How do living things come to be? But it was wrong. But it was rational and it was reasonable based on limited information, right? Here's how has anybody ever heard of spontaneous generation? basically what spontaneous generation said is that non-living things can give rise to living things. So like a rock can give rise to something that is alive. Now, how many of you guys think that that is pretty close to preposterous? Be honest. You're kind of snickering a little bit, right? It's, you kind of have this sort of reaction like, how can an actual intelligent person actually believe that? I can guarantee you there were well-educated people in the 19th century who were signed on to this idea. And I love to use this as an example of a cautionary tale in science, because spontaneous generation wasn't just created by a bunch of half-wits. It was actually created by the scientists of the day. Here's how it works. If you have a piece of meat on the table and you just leave it there, because back in the day, there was no refrigeration here, right? So you just leave it there. Then all of a sudden you see a bunch of worms in it. And you were watching this pretty closely. You didn't see any worms crawl up to it. No worms dropped on it, right? I mean, you didn't see where these things came from. They just kind of appeared. They just kind of spontaneously generated. So maybe there is some sort of an unknown mechanism by which the meat was able to spontaneously transform into worms. Does that sound crazy? No, not necessarily. Think about it for a second. I can give you an example of a crazy spontaneous transformation that actually is real. Think about it. There's an ugly little caterpillar crawling around. That's a giant, ugly looking beast. And then all of a sudden it goes into this like little sleeping bag thing. And then out comes what? A butterfly. Does that butterfly have any resemblance whatsoever to the caterpillar? At their level, no. I mean, you can see the vestiges of the caterpillar and the butterfly, but that's a scientific study of the butterfly. From a general view of that, what you have is two unrelated things. And one spontaneously transformed into the other. That was evidence of a living thing spontaneously generating into another living thing. Is it such a leap in logic to hypothesize that there's a mechanism for a non-living thing to spontaneously generate into a living thing? In the absence of evidence, it's a viable hypothesis. Because remember, at this point, you don't know anything about entomology. You don't make the connection to the housefly landing on the meat and laying eggs that are subvisible on the meat itself. You don't even know anything about the fly's life cycle. There's no entomology at this point. So you don't know that they're laying eggs. You don't know that the fly actually has a larval state, that all insects actually have a larval state. And that's what the maggots are, the larval state of the housefly. So you don't have any of that knowledge whatsoever. All you see is nothing, and then you see something. Question.
But where did where did we think, I guess, because obviously, like where the first cell ever came from?
Nobody knows. Evolutionary biology tell you they know, but they're lying. Nobody really knows. We have stories. We have stories and yarn spin to kind of postulate and hypothesize what may have happened, but nobody knows for sure because nobody was around. So it's impossible to know for certain. We have a couple of good ideas that sound good, but like this one sounded good. This one had legs, but it turned out to be wrong. All right. So, and we have a lot of those, by the way. This is the reason why I always start off the semester by saying never fall in love with your idea to the extent that which you can't question it and basically change it, right? Because you may be the spontaneous generation person who just hasn't been proven wrong yet, okay? But it is wrong, right? So where did we finally get rid of this one? It's around this time, actually, in the 19th century. Actually, Louis Pasteur of pasteurization fame. That's what we do to our milk. Actually had to invent, he's the father of microbiology. He actually had to invent sterile techniques, which actually they do in this room in order to, by the way, you guys have been doing it through COVID. So like all of your distancing, like not touching anything, not having like hard surface touching. So gloving up, masking up, covering yourself up, washing, sterilization of everything, that's all sterile technique. So he didn't necessarily know a lot about bacteria, but he knew that there were things that he couldn't see that were problems. And the only way to sort of defend yourself against it is to be ultra psychotically clean. And it wasn't until he introduced that sterile technique that he was able to finally debunk spontaneous generation. But I can tell you right now, there were well-educated people in this day and age who probably were on the spontaneous generation list, who probably believed in it. The other thing this also tells us then is just like a puppy comes from dogs, right? Is that there is a continuous line of descent, right? Just like basically our line of descent goes to our parents and then to the grandparents and great-grandparents and so forth. And that cells basically form a line of descent. Now, when you think of the term descent, what do you think of? Like what field of biology do you think of? The study of descent is what? What? Not physics. We actually have a chapter on it later in the semester. What? Generations, right? So that's part of the descent thing. So we have it. What? DNA, that's also part of it. So if you put all that together, what? Genetics, bingo, right? The study of descent, which is the study of generations and DNA over generations, is genetics. So basically, when you're talking about descent, a line of descent, that is one cell is related to another by a line of descent, you're talking about genetics, the transmission of DNA from one generation to the next. As a matter of fact, Darwin, in his paper, actually mentions, makes a phrase that he uses a lot when he describes evolution, and he calls it descent with modification. So when he's talking about species changing into another species, it's descent, that is to say the passing on of DNA, with modification, the modification of that DNA to give you different types of traits. And so at the heart even of evolution is descent. What does that mean? That means that even at this point with the cell theory, you're already laying down this idea that you have this transmission of information, genetics, that is sort of at the core of all of this. As a matter of fact, Darwin himself even admitted that what he's looking at is a genetic phenomenon. That in order to get transmutation of species at all, he requires genetics. And that at the beginning, even in the beginning, evolution has never been about fossils and rocks and any of that nonsense. It's always been about genetics. It's just that we didn't have genetics yet. This is the reason why, unfortunately, after Darwin published his paper, it just basically kind of became philosophical. All the atheists took a hold of it, and they just decided to use it as a tool to bash anybody who doesn't, who's not atheist, which is really unfortunate because basically what they did is they pretty much destroyed a really fascinating, interesting scientific idea for their own theological purpose. So, and that kind of pisses me off actually. So, well, it does, because as soon as you do that, then nobody else can touch it, and you're not welcome unless you're willing to sign on to a theological concept, which is completely, absolutely inappropriate, because it's a genetic idea. Now, genetics doesn't come along after Mendel, until Mendel comes around 1865. So it's about 15 years after. And that's when we're able to start the process. And actually, that took a long time for us to really understand enough genetics to now, where we have genomics, that is entire genome sequence, we're for the first time able to go back to evolution and then take a look at this the way it ought to have been looked at the get-go, which is from a genetic standpoint. This is one of the reasons, by the way, and I'm a molecular guy, so obviously expect this from my bias. This is the reason why I have absolutely I'm not really all that impressed with a bunch of bones. Paleontology to me is like one of the most pathetic fields of science, because all it tells you is that, oh yeah, there's just a big pile of things here that didn't make it. and they're not here anymore. Great, that's about it, right? So if you really want to understand the relationships, which is what they've been trying to do all 19th century, they just can't do it, is because they didn't have the right tool. You know, it's like basically trying to unscrew a screw with the wrong screwdriver. It's like you can kind of get to it, but not really, right? Because you have the wrong tool. Well, for the first time, we have the right tool in genomics. And we can now go back and revisit evolution from a genetic standpoint, not from a paleontological and geological standpoint, because those have never actually been helpful, honestly, to evolution. And it really creates kind of a bifurcation of the idea, right? Because a lot of times people kind of toss evolution with, you know, old Earth and that sort of thing. So they're really two separate ideas. The age of the Earth is a completely separate theory from evolution. They're not the same. Okay, and that's and you can see that though. You can see the threads that are weaving into it, starting to work their way into it, and then they just start getting tied together. And so you can kind of see the beginnings of it. Okay, so let's take a look at cell size. Now, cell size is limited, right? So the size of the cells is pretty tiny. They're all microscopic. And so oftentimes the question, the students will come up with the question of, like, that's great and good and all, but why is a cell tiny, right? Why don't you have a big giant cell, right? That's a reasonable question. Well, we know why, because when you're a cell, what you're doing is you're basically basing everything you do on the process of diffusion. And basically the way you get things into the cell and the way you get your waste out of the cell is all by diffusion. So when you take a look at diffusion, diffusion is basically the process of the movement of solute from an area of high concentration to low concentration. That's all it is, right? Remember the example we used in lab when we kind of sketched out diffusion? Remember we said you put the little drop of food coloring in a glass of water, what happens? It spreads out, right? So where would the high concentration be? So in the drop itself, right? And then the glass of water would be low, right? So it's naturally flowing from high to low. That's the reason why it flows from an inward to outward pattern. And then when does it stop? Yeah, so the whole glass will be kind of like a uniform color, kind of a light pink color probably, depending on how much you put in there. And then there's no more diffusion, right? So that's called equilibrium. And so diffusion will always move from high to low until you reach equilibrium. But here's the problem. Diffusion is limited by several different things. The biggest one is it's distance limited. So think about it this way. If I have a bottle of perfume, and I'm going to stand over here in the corner, and I open it up, who's going to smell it first? Right? So you're going to get it first. And then who's going to get it last? Who's going to smell it last? You guys in the back, right? So if you notice, where's the high concentration of the perfume? It's in the bottle, right? And where's the low concentration? It's out there. So you notice that if I have, let's say I have Betsy instead of sitting over there. Let's say I have her just like stand just on the other side of that wall outside in the hallway, right? And the door's open. And then I uncork the bottle. How long is it going to take for her to smell it? She may not, right? Why wouldn't she? Well, it's spread out. So assuming like I have enough, that there's like a big bunch, so it's not going to equilibrate. So why wouldn't she smell it? Why would she be standing over there across the hallway and not smell it? What would cause that? What? It doesn't travel, right? Well, it does travel, right? Because
By the point it's spread out that much, the amount of it in the air is.
so basically you're saying that where she is maybe too far away, right? So now think about this. If life and death depended on you smelling this perfume, then who's going to live? Well, you guys are in good shape, right? You guys going to take a little bit longer, but you're going to be able to smell it, right? So if Betsy's way out there, unfortunate Betsy, does she get to live? No, because she's exceeded the limits of diffusion, right? This, by the way, is one of the reasons why you're small. Because you have to be small. If you choose to do business by diffusion, you're choosing a decision that has consequences to it. That consequence is smallness. So what does that mean? Well, basically, when you're taking a look at making early decisions, and a lot of times students will kind of think about this, right? They'll think about a cell and they'll be like, okay, so at some point you decided to be small. It's like you kind of showed up and you'd be like, well, I want to be a small cell, so I'm going to be small, right? And then you kind of work with that. That's not the way it worked. You didn't choose to be small. You didn't choose to build the structure of your body the way it's built. You didn't make any of those choices. That's kind of the way we think about making choices, right? We make consumer-based choices. We want it to look like this, 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 and this. Now let's go do what we need to do in order to make it look that way. That's not the way it worked. When you're talking about life, the decisions are made on the opposite end. Remember, the decisions you're only making are basically the big biological questions. Those are the decisions you're making. Those are it. That's it. So you're not making as a cell a conscious choice to be big or small, or to be multicellular or not. All you're doing is making a decision based on your big biological question of life. So for instance, how do I get stuff in and out of me? So you got a couple of choices there, don't you? The cheapest version is diffusion. You don't have to do much for that. It pretty much is for free. It's pretty cost effective. But if you choose that pathway, then you have consequences to that choice. The consequence of that choice is that you will only be small. You cannot be a gigantic organism if you choose diffusion. Melissa. No. Oh yeah, sure. Yeah, sure. No, I mean, you have cells. I mean, they can get bigger, but they can't get that much bigger because they'd be violating this, and they're just too costly to make them bigger. We'll talk more about that actually in the next slide. The consequences are bigger. It's very negative in nature. But a good analogy to this is career choices, right? I mean, so here's a good example. I've made a career choice to teach. And so that was a choice that I made early on because this is what I wanted to do. However, that career choice has consequences to it, doesn't it? Some of the consequences means I'll never be famous, which is one that I'll live with. It also means that I'm never going to be rich, right? I mean, this is about as good as it gets. So some of those consequences are, you know what I can afford to drive is a 15-year-old Ford Escape. Now, that's just the consequences of what I've chosen to do. So that choice that I made early on had consequences to it. Had I wanted a different outcome, then I had to have made a different choice. So simply put, I will never own a Bentley because I simply just didn't have a choice that supported that level of income. I don't play for the Denver Broncos. Never could have actually, because I'm just not the right body shape and type. unless I'm a kicker, I guess. The assistant to the kicker, that's what I'd be, right? I'd massage the kicker's leg, that's about it, right? But right, so those are the consequences. If I wanted the Bentley, then I had to make different career choices, get a different education, and make more money to be able to support that. So the decisions we make actually have consequences to them. Those consequences is what defines our reality. And that's the same thing that's true here, right? So the decision that the cells make to be able to do things at a cost-effective manner, by diffusion, means that they will never be big, because you just can't support bigness with diffusion. So let's take a look at it. And by the way, that's true for everything, right? Whenever you look at structure, it's not like, oh, hey, let's build the structure. No, you never did that. What you did was you walked up to it and you said, you know what? I have to be able to do this. So what can I do to do this, right? What can give me this? This is what I need to accomplish. This is the function that I need to do. So what can get me there? And anything is on the table. You can build anything you want, right? You just have to do the function. And there'll be like maybe a half dozen different versions of a structure that can do that function. They can be quite different from each other. But guess what? That's what creates diversity in an organism. Is I may choose to build this structure to satisfy my function, but you build something completely different. That makes you a different species, right? And so those are the sorts of things that we make. That's the reason why those big biological questions of life are important, because as we sit down to answer those big biological questions of life, it creates decisions that then have consequences down the line that turns us into what we are. Okay. So let's take a look at the rate of diffusion and see what it's affected by. So first of all, we know about distance. We know that the rate of diffusion will go down as your distance goes up. So the further away you get, right, the less your diffusion. We also know that surface area will increase your diffusion rate. So surface area is the total amount of area that you have to diffuse across. Okay, so that'll increase your diffusion rate. Temperature will also increase your diffusion rate. That's true because the molecules will move faster, so they're able to diffuse faster. But that's not really functional for us, is it? Because temperature is one of those things that we have to kind of control and regulate from the environment, because otherwise it's very easy to kill ourselves with it, right? Because we just talked about denaturing proteins with temperature. So it's kind of, you don't want to play with that fire, right? So that's probably not your best strategy for diffusion rate. Another big one is concentration gradient. So your diffusion rate will increase with increasing concentration gradient. So what does that look like? So remember, if you're going from high to low, then what that means is on one side, you're going to have a concentration. The high concentration is going to be really high. The low one is going to be really low. That gives you like a really steep incline. Just like if you were to roll down that hill, you'd be rolling fast, right? If you soften that incline, where your high is here, but this is now your low. Now you have a shallower incline, so you're not going to be moving quite as fast downhill. Then, of course, if your two concentrations are equal, this is basically fast, slow, and no flow. So this is equilibrium. This is the pink. That's the pink glass, where everything is uniform. All the concentrations are the same. So what does this mean? So what this means is you can manipulate the rate of diffusion, can't you? Even if you just use this idea, the steep versus the shallow incline, this is kind of like one of those little marble puzzles that you kind of get, right, with a little table with like a little maze in there, and your idea is kind of get the marble to kind of go through the maze, right? And what do? If you want the marble to go that way, you tilt it up, right? If you want it to go very slowly, you give it a gentle tilt. If you want it to really go, you tilt it steeply, right? So you can change the velocity of the marble as it's moving around by changing the pitch of that tilt. Right? Same thing's true for diffusion. You can change the pitch of the concentration gradient to get you different speeds of diffusion. So things can trickle out very slowly, or they can just rush out like gangbusters. Okay, that gives you a lot of control over that. So even though you're small, you have a lot of potential variables that you can use to control the flow of diffusion itself. Okay, so let's take a look at that first one. And let's kind of unpack that one a little bit. So we want to take a look at surface to volume ratio. Now, surface area is important because this is basically where you do work. And the volume is basically the size of the cell in 3 dimensions, where the cell does work. So surface area, because you can do work on the surface area, represents a benefit. That's a good thing. The more work you can do, the more you can get accomplished, the more likely you're going to survive. Volume, on the other hand, is materials cost. This is overhead. So this represents a cost. So when you take a look at surface area to volume, you don't just look at functionality of the cell, but you look at the functionality of the cell relative to how much it costs you. Okay. And just like a frugal shopper, your cell is always looking for maximum benefit with minimum cost, right? So let's go yard sale shopping, right? Right. So that's where you can get stuff at minimum cost. So this is an important thing, right? Because the idea is if I need more working surface, then what can I do? Well, I need to increase my surface area. And so the common idea would be like, well, if I need to increase my surface area, then why don't I just increase its volume, right? Because if I increase my volume, I will increase my surface area. The problem is the volume increases a lot more. So even though you do get more surface area, you also get a lot more cost. So the question is, how does this work? Well, this also has the effect of limiting your size. This kind of gets back to the size question Melissa was talking about, right? So this idea of why don't you just make it bigger? Well, because that's a cost. Making things bigger gives you more cost. And the question is, you only make it bigger if it's accompanied with a good deal, right? That is, if I get a lot of surface area for that cost. But as it turns out, you don't. So to drive home that point, I want to do this comparison. Now, we have 2 different cells here, little guy and big dude, right? So we're going to take a look at the cell radius, and it's not, it's just relative, so we're just throwing stuff out there, right? So here you have a cell that has a radius of 1. If you look at the radius is basically just the straight line from the center to the edge, but it's 2-dimensional in nature, right? Remember, the cell is 3-dimensional, so we can't just look at radius. You got to look at all 3 dimensions because there's all 3 dimensions of cost in here. But what we're going to do is we're going to increase the radius 10-fold from 1 unit to 10 units. And then we're going to ask the question, did we get a good deal? Right? That's what we're going to do. Well, here's the question. Well, let's take a look at your surface area, right? We don't know that unless you take a look at your surface area. So like if I say, okay, I spent $20,000 on a car. Was that a good deal? Well, it depends on the car, right? I mean, if it was a Bentley, then yeah, it was a good deal, right? But I mean, if it was a lawnmower, then no, right? It wasn't a good deal. So it depends on what you got for that cost. So we're going to take a look at the surface area, which is 4 pi r squared. And you can see that our initial starting units are 12.57. And by increasing your radius 10-fold, you get up to 1257. Not bad, right? That is what? 100-fold increase in surface area. So far, so good, huh? That's not too bad. But remember, it's not just surface area. You do get more surface area. The question is, how much cost did you have to incur to get to that surface area? Well, now we have to look at volume. So here's your benefit. Now we have to look at the true cost, which is 3-dimensional. Right? This is the reason why we have to get volume and not just radius, right? So 4/3 pi r cubed is going to be your volume. And by the way, I'm never going to have you calculate the volume of a cell on an exam. That would be kind of more like biophysics, things like that. That would be a mean class. So that would be different sort of a creature. So here we have basically in volumes, we have 4.189 units. As we increase our radius tenfold, it gets us up to 4189. So what is that? That's a 1,000-fold increase. Is that a good idea? No, because you are tenfold in the hole, aren't you? Because you got 10 times more of a worse cost than benefit. So when you take a look at surface area to volume ratio, you can see that initially it's at 3, but then when you increase it tenfold, it actually goes down to 0.3. So this is a bad deal. This is kind of like 5 for the price of 10. Is that a deal you're going to take? No, right? Would you buy 5 for the price of 6? No, because you're still buying more than just define them all by themselves, right? So that's a bad deal. That's exactly what's happening here. So here's the problem then. You need more working surface area. How do you get it? How do you get it and manage your costs? Well, the cell does a lot of cute little tricks. So here's an example of just one little trick that the cells oftentimes will do. So here's a rectangular cell, and it's basically kind of linked to other cells over here. So we're just going to look at this surface here. So that is your working surface. That's your surface area that you're doing your work on. The others are blocked by other cells that you're attached to. So the question is, you want to increase your productivity there. How do you do it without incurring extra costs? It's very simple. What you do is you dork around with your plasma membrane. You do silly things like this. Now for roughly the same volume, you've increased your surface area. Why? Because instead of working just on this straight surface here, now you're working on all of this. So you basically increased your working surface area, but you haven't really changed your volume. The reason why I mention this, and I drive this home, is because biology is rife with cellular structures that are specifically designed to increase surface area. That's an economizing tool. That's your cell basically making do with what it's got and repurposing what it's got and kind of increasing its productivity. Okay. For no cost, right? So that's cell size. Now let's take a look at microscopy and some microscopes. So basically, when we take a look at microscopes, obviously we worked with one, right? When we did lab 5 and 6, we worked with one, worked with the light microscope. And basically the light microscope, the job there is to essentially make small objects look visible to us. Generally speaking, from the naked eye, you can only see things that are in the 100 micrometer range. Most of our organisms are less than 50. So obviously they're subvisible. And so what microscopy actually does is it basically changes or increases what's called resolution. Now, resolution is your ability to be able to discern 2 individual points and to distinguish them as 2 separate points. And here's an example. It's kind of a difficult room to do this particular experiment in, but I'm going to try it anyway. I'm going to pick on Melissa. I promise I won't kill you, Melissa, like I did with Betsy. So this is what it means to have resolution. Here's 2 spots. Can you see them as 2 separate spots? So that's good resolution. I'm going to put them now closer together. Can you see them as 2 separate spots? Getting harder? Yep. Now I'm going to do, can you see them as 2 separate spots now? Kind of looks more like a dash probably. Okay, Malaysia, can you see those 2 separate spots? So what we've just done is we've defined the line of resolution. We're losing it somewhere in the middle of the classroom. Okay. So So what microscopy does then is it basically takes this image and puts you like a microvision. Basically, put you right up next to it so you can see clearly those two individual points. Okay. That's basically what resolution is. And that's what microscopy does for us. So we have two different types of microscopy, right? We have light microscopes, which we used. And when you take a look at a light microscope, the one thing to really, in all microscopy, the important thing to always understand is that when you're looking at microscopy, you use a particle of resolution. In this case, the light, that is a photon of light, is the resolving particle. But this also limits your resolution. Your resolving particle always limits your resolution. What does that mean? That means as long as our sample is bigger than a photon of light, then the light will basically glance off of that, and then we'll be able to see it. And that's exactly how I see you guys. I'm not actually seeing your physical self. What I'm seeing is light reflecting and bouncing off of Alan, and that's basically what I'm seeing, is I'm seeing the light. Okay. And so what if, however, your sample was smaller than a photon of light? Like, here's my sample, here's my photon. Then what's going to happen is there's not going to be any glance off. So there's not going to be anything to detect, because basically the photon of light just sort of swallows up the sample and it doesn't reflect off. Okay. So that represents the limit of my resolution. So you're limited by the size of the photon of light. This gives us a resolution power, though, with light microscopes to about 200 nanometers. Not bad, right? Going from 100 micrometers down to 200 nanometers. That's a pretty good improvement. So light microscopy is actually not bad, especially these days. However, what if we want to see tiny things, right? Because after all, I mean, you guys saw eukaryotes, right? And you saw like the little organelles inside them. They look like little bubbles. You didn't necessarily know what those organelles were, but you knew that they were organelles of some sort because there were little bubbles inside these guys. What if you wanted to actually look up close and personal at those little bubbles? Well, you're not going to be able to use light microscopy because the photon of light is just too small or too big, right? So you need a smaller resolving particle. Well, how about an electron? So in electron microscopy, the electron is the resolving particle. And of course, how big is an electron? Small. Is there anything bigger than an electron? I mean, smaller than an electron? Well, yeah, subatomic if you, but we're not going particle physics here.
No, good no.
Yeah, even a proton, right, is bigger. So theoretically speaking, you should be able to bounce an electron off of a proton and be able to see a proton. Yes? I'll get back to that in just a second. So basically speaking, because you have this very tiny resolving particle, it allows you to be able to bounce electrons off of the sample. With the electron as your resolving particle, you get down to 0.2 nanometers, even better. Okay. Now, getting back to the proton question, a lot of times students will ask, well, wait a minute, if an electron is so small and it's smaller than a proton, then does that mean we can use electron microscopes to see protons with? The answer is no. And it's not because of this here. It's not because of resolution physics. It's because of a different type of physics that we deal with in particle physics, which is quantum mechanics. The reality of it is that most of our existence, most of our reality, even down to light microscopy and the upper ranges of electron microscopy, is governed by the principles of relativity, which is a set of universal physics that sort of governs the way that we think about the universe. It's very predictable. It's very calculable. This is what Einstein is most famous for. It's not what he won his Nobel Prize for, but it's what he's most famous for. But what we noticed is that also around Einstein's time is we noticed that when we start to look at things at the atomic level, it's like the entire universal rule book changes. And it switches from a relativity-based reality to a quantum mechanics-based reality. And in quantum mechanics, it is full of unpredictability and paradoxes and a lot of head scratchers, and things don't behave the way that we would expect them to behave. So it's very unpredictable and it's very difficult to figure out. And this is the reason why you can't look at a proton with an electron, is because quantum mechanics is just a squirrely thing that just kind of makes that impossible, right? When you're talking about this here is relativity, right? When you're talking about the atomic level, you're talking about quantum mechanics, and they're completely different worlds, okay? And by the way, the rub between quantum mechanics and relativity has befuddled more than a few great minds, including Einstein himself. And we still are scratching our heads over quantum mechanics. It's a fascinating and befuddling area that we're learning more about, but it's still crazy. It's a crazy world. It's kind of like going into Wonderland, right? Where everything just doesn't make any sense anymore, right? So with electron microscopes, then we can generate two different types of images, and we'll see lots of those throughout this chapter. We can run a transmission electron micrograph, which basically takes a sample and beams electrons through it, through like a cross section of it. And we can do a scanning electron micrograph, which basically you take a specimen and you glance electrons off of it. And this kind of gives you a three-dimensional surface view of your sample. So this kind of gives you a range of your visibility. So you can see you got the human eye down to about 100 micrometers or so. Light microscopy will go from a millimeter all the way down to just maybe about half a micron or so. Electron microscopy, you notice there's a big overlap here. So even though you can see prokaryotes, it's very difficult to see that, right? You guys remember looking at lactobacillus, and they look really, really tiny. So in order to get a really up close personal look, you want to go from a very poor resolution particle to a much better resolution particle. And so a lot of times, a lot of our electron microscopy was basically taking a look at some of those things we can't see with light microscopy, but we're going to get a bigger, more detailed picture of it. Okay? So we can actually see the shape and structure of some of these organelles. So here's a different type. I'm going to give you a quick rundown on these. So basically, bright field is your light microscopy. That's what you guys have been using. So it uses a condenser lens that basically helps to focus some of that scattered light, and then beams that through a sample. And then you kind of see the shadow play and the way the light bounces off of it. So this is your bright field. This is like normal microscopy. A variation of that is what's called dark field. And so basically this has a specific condenser where it kind of blackens out the background, and it just lets a little halo of light come through. So what happens is you kind of have this photonegative effect where the organism kind of glows, but on a black background. It's actually pretty cool. And then you have phase contrast. This basically uses the wave particles or the wave property of light to kind of bring waves into phase with each other and out of phase. So they're kind of like aligned with each other or not aligned with each other. And so you can get this phase contrast, which creates a lot of different types of shadow play and different kinds of nuances, the way the light kind of works through it. Then you have differential interference, which is this one here. So this one is also using the wave-like patterns of light. So in this case, what's happening is you can sort of align your waves together, trough to trough or peak to peak, to get an amplified signal, or you can have them cancel themselves out. Here you're using polarized light, so you're polarizing the light itself, and it kind of creates a sort of bas relief with organelles. This is one of my favorites, actually. It's really cool. It's hard to get a hold of, but it's really cool. And then these two guys here are related in the sense that these guys are fluorescents. So remember we talked about fluorescence in chapter 2, or fluorescence is just the process of high energy light exciting electrons. As the electrons absorb that energy, they jump up to a higher energy level. And then when they drop back down, they emit that excess energy in the form of a photon of light. That's fluorescence. Well, in this case, what we've managed to be able to do is to take a protein, and we were able to tag this protein with a fluorescent molecule. And what this has done is it's allowed us to be able to study this protein, where it is, how much is made, when it's made, like when in the cell's life cycle is it made, and those sorts of things. So it's allowed us to be able to watch the protein and study the protein very, very carefully. And so here you can see you've got this yellow protein, which has this yellow fluorescence molecule on it, and we've been able to highlight wherever it is in the cell. It tells us a lot about it. And so we just, all we have to do is just basically tag this protein, and then all we have to do is beam that UV light on it, and then it'll fluoresce by absorbing the energy, and then the electrons fall down and they emit that photon of light. Now, generally speaking, we'll just use like a UV lamp for this particular purpose, so that we can beam enough high energy light in there. However, remember, scattered light is the enemy of resolution. So one of the reasons why you can see things clearly is because your eyes actually are able to focus light into a sharp beam that allows you to be able to determine good resolution with your eyes. So what happens if light gets scattered? Well, you see things in a fuzzy way. It's like not a very sharp image. So what is the most focused type of light? It's a laser, right? A laser is a sharp beam of photons that's about as sharp and focused as we can get. So because there's zero scatter in a laser, what it does is we're able to basically shoot this high energy light. Like we can actually pick a frequency of light in the laser and shoot the fluorophore. So we're doing the same thing, only now because it's a very focused piece of light, it's going to be much sharper in resolution. So you can see how clear this picture is. And this is what's called confocal microscopy. It's also a type of fluorescence microscopy. But what makes it really stand out is the fact that it uses a laser. It really doubles down on the focus of light to get you that. Very expensive systems. But very, very worth it. They give you some really, really breathtaking pictures of protein. So really you can see the same protein, but now you can kind of see it in a much clearer type of image. And then you can get more detailed information from that. So confocal systems, the Anschutz definitely has one. Boulder probably has one. I don't know that there's one on this campus because these tend to be pretty expensive and it takes a lot of maintenance. They're usually a lab does not have one. Usually multiple labs go in on one. That's what happens. Then we have electron microscopy. So with electron microscopy, you can see you have the beam through of the electrons going through the cross section of your cell. You can see all those like little circles in there. Those are the organelles. And this is actually not very strongly focused. You can actually get much closer than this with the electron microscope. We'll see actually examples of these throughout the chapter as we get there. And then, of course, you can see the scanning electron micrograph. So this is basically that little glance off of the surface. So you can see what looks like a bacterial cell clearly on the outer surface of that little bacterial cell. So you can see very, very informational. Matter of fact, these electron micrographs has really given us the knowledge that we have now today of our cells. So cell biology is largely built on the back of these electron micrographs. So let's start off, first of all, with the basics, right? Let's start off with, we're going to start off with prokaryotes first. We're going to talk a little bit about cell basics, about cells, and then we're going to talk a little bit about prokaryotes, and then we're going to use that knowledge of prokaryotes to go into eukaryotes. And that's a pattern we see throughout the semester, is we always talk about a mechanism from a prokaryotic simple system, and then we sort of transfer that knowledge to the eukaryotes and expand on that. So a couple of things that cells all have. Let's start there, right? So what does all cells on the planet have? Well, first of all, they have to have genetic material, and typically centrally located genetic material, right? Why? Because your genetics, right, your DNA is your master blueprint, right? All the information you need to build you from scratch. So therefore, if you're alive, you have DNA. DNA equals life, okay? Now, that's one of the markers of life. So if we see something with DNA in it, we'd be like, oh, okay, you were alive, right? Because you have to have all that information to build you from scratch. Another thing you have to have is cytoplasm. And so cytoplasm, there's a couple of terms here that I want to sort of clarify. So first of all, the term cytoplasm and the term cytosol. So cytosol basically refers to the fluid portion in the cell, whereas the cytoplasm is the organelles plus the fluid. Now, I can tell how old you are in biology by which one of these terms you use. So if I hear somebody use the term cytosol, I can tell that they're an old codger because this is an older term. Or I can tell you learned your biology from an old codger. Because generally speaking, cytosol was an older term that we used to use when we made the distinguish between cytoplasm and cytosol. Because we used to think that inside the cell, you had these vast expanses of fluid and an occasional organelle here and there. As it turns out, the case that is not true, right? It's actually choked with organelles, so you don't really have a lot of open fluid at all. As a matter of fact, most working cell biologists, even the great Catherine Howell, who actually works at Anschutz, herself doesn't usually use the term cytosol. She uses the term cytoplasm. The only time I've heard her use cytosol is when she's very specifically trying to draw a distinctor between cytoplasm and cytosol. She's specifically talking about the fluid of the cell. But generally speaking, most biologists will be like, oh yeah, it goes into the fluid of the cell, right? So then you say use the term cytosol. It's an older world term. And of course, you have a plasma membrane with your lipid bilayer, which is what forms the boundary within which your cytoplasm exists. Right. I want to add a fourth one on here. Ribosomes. These are basically protein factories. That make protein. Another one of those circular moments in evolution, right? Chicken egg questions. So if your protein factories are themselves proteins that make proteins, and where do the proteins come from to make the protein factories, right? So you can see there's an evolution has almost no way out of those. So they just, it's like one of those soft spots where it's like, I don't know. Nobody knows, right? We have a lot of ideas, we have a lot of yarn spinning, but nobody really knows, right? That's the chicken or egg thing. So let's take a look then at the prokaryotic cells. And since we are just about at our witching hour, I got 1 minute on that clock and right about there on this one. This is a good place to start clean because we've got a couple of slides here to work on prokaryotes before we segue into eukaryotes. So what we'll do is we'll start moving then toward a more specific look at prokaryotes. We'll talk about a few things for prokaryotes and we'll move into eukaryotes. And I got a big old outline to draw. And then we'll do that, however, on Thursday for you guys.